Have you ever wondered what your life would be like if you had made a different decision at a crucial moment? What if you had chosen a different career, a different partner, or a different path? What if you had a different personality, a different appearance, or a different destiny? Would you be happier, sadder, richer, or poorer? Would you even recognize yourself? These are not just hypothetical questions. They are the basis of one of the most intriguing and controversial ideas in modern physics, parallel universe theory. According to this theory, there are countless other worlds that exist alongside our own, each with a different version of reality. Some of these worlds are very similar to ours, while others are radically different. Some of them may even contain another you, living a completely different life. But how can this be possible? How can there be more than one universe? And how can we know if they exist? These are the questions that we will explore in this video. We will look at the different types of parallel universes that scientists have proposed, and the evidence or arguments for each one. We will also examine the implications and challenges of parallel universe theory, and how it could change our understanding of ourselves and our place in the cosmos. Welcome to Spaceverse. Let's begin our journey into the parallel universe theory. Before we talk about the different types of parallel universes, we need to understand how the universe began and how it evolved. According to the most widely accepted theory, the universe started with a singularity, a point of infinite density and temperature that exploded in a massive event called the Big Bang. This event created space, time, matter, and energy, and set the universe on an expanding course. However, the expansion of the universe was not smooth and uniform. In the first fraction of a second after the Big Bang, the universe underwent a period of extremely rapid and exponential growth, known as inflation. During this period, the universe expanded by a factor of at least 10^78, or about 100 trillion times. This means that a region of space smaller than an atom became larger than a galaxy in a blink of an eye. But why did inflation happen? And what caused it to stop? The answer lies in a mysterious form of energy called the inflation field. This field had a very high and constant value throughout the universe, and it acted as a repulsive force that drove the expansion. However, the inflation field was also unstable, and it eventually decayed into other forms of energy and matter, ending the inflationary phase. This process is called reheating, because it raised the temperature of the universe and created the conditions for the formation of atoms, stars, and galaxies. But here is the catch. The inflation field did not decay uniformly and simultaneously everywhere. Instead, it decayed randomly and gradually, creating bubbles of space where inflation ended and reheating occurred. These bubbles are called pocket universes, and they are separated by regions of space where inflation still continues. This means that inflation never stops in the whole universe, but only in some parts of it. This is the essence of eternal inflation. The universe is constantly producing new pocket universes, each with its own history and physical laws. One of these pocket universes is our observable universe, the region of space that we can see and measure. But there are countless others, each with different properties and outcomes. Some of them may be very similar to ours, while others may be radically different. Some of them may even contain another you, living a completely different life. This is the idea of parallel universes, and it is one of the most fascinating and controversial implications of eternal inflation. Before we talk about the many worlds interpretation, we need to understand some of the basic features of quantum mechanics. Quantum mechanics is the branch of physics that describes the behavior of the smallest particles and forces in nature, such as electrons, photons, and atoms. Quantum mechanics reveals that the physical world is not as deterministic and predictable as we might think. Instead, it is full of uncertainty and randomness, where nothing is certain until it is measured. One of the most famous examples of this is the Double-Slit Experiment, where a beam of light or a stream of electrons is sent through two narrow slits and then detected on a screen behind them. According to classical physics, we would expect to see two bright spots on the screen, corresponding to the two slits. But what we actually see is a pattern of bright and dark fringes, called an interference pattern, which shows that the light or the electrons behave like waves, not like particles. This is surprising enough, but it gets even weirder when we try to observe which slit each particle goes through. If we place a detector near one of the slits, we find that the interference pattern disappears, and we see two bright spots again. This means that the act of observation changes the outcome of the experiment, and that the particles somehow know whether they are being washed or not. How can we explain this phenomenon? One way is to use the concept of the wave function, which is a mathematical function that describes the state of a quantum system, such as an electron or a photon. The wave function tells us the probability of finding the system in a certain location, with a certain momentum, or with a certain spin. The wave function is not a physical thing, but a representation of our knowledge of the system. When we measure the system, we find out one of these properties, and the wave function collapses to a single value. For example, if we measure the position of an electron, we find out where it is, and the wave function becomes a spike at that location. Before the measurement, the electron was in a superposition of all possible positions, meaning that it had a certain probability of being anywhere. After the measurement, the electron is in a definite position, and the probability becomes 100%. But this raises a question: what happens to the other possibilities? Where do they go when the wave function collapses? And what determines which possibility becomes reality? This is where the many worlds interpretation comes in. The many worlds interpretation, proposed by Hugh Everett II in 1957, suggests that there is no such thing as wave function collapse. Instead, every time a quantum measurement is made, the universe splits into multiple branches, each corresponding to a possible outcome of the measurement. In each branch, the wave function remains intact, but it is different from the wave function in the other branches. This means that there are multiple copies of the observer and the system, each experiencing a different reality. For example, in the double-slit experiment, there is a branch where the electron goes through the left slit, and a branch where it goes through the right slit. In each branch, the observer sees a different result on the screen, and the interference pattern is different. The branches do not interact with each other, and the observer is not aware of the existence of the other branches. According to the many worlds interpretation, the universe is constantly branching into new realities, creating a vast multiverse of parallel worlds. In each world, there is a different version of you, living a different life. Some of these worlds are very similar to ours, while others are radically different. Some of them may even contain another you, living a completely different life. This is the idea of parallel universes, and it is one of the most fascinating and controversial implications of quantum mechanics. Before we talk about the holographic principle, we need to understand the concept of infinite space. Infinite space means that the universe has no boundaries or edges, and that it extends forever in all directions. This is one of the possible models of the shape and size of the universe, based on the current observations and measurements of the cosmic microwave background radiation, the relic of the Big Bang. However, infinite space does not mean that the universe is infinitely old or infinitely large. The universe is still about 13.8 billion years old, and it has a finite amount of matter and energy. This means that the universe has a finite density, or the average amount of matter and energy per unit volume. The density of the universe determines its curvature, or how much space bends due to gravity. If the density of the universe is equal to a critical value, then the curvature of the universe is zero, and the universe is flat and infinite. If the density of the universe is greater than the critical value, then the curvature of the universe is positive, and the universe is closed and finite. If the density of the universe is less than the critical value, then the curvature of the universe is negative, and the universe is open and infinite. According to the latest data from the Planck satellite, the density of the universe is very close to the critical value, within a margin of error of 0.4%. This means that the universe is either flat and infinite, or very slightly curved and very large. In either case, the universe is much larger than the observable universe, which is the region of space that we can see and measure. The observable universe has a radius of about 46 billion light-years, and it contains about 10 to the power of 80 atoms and 10 to the power of 11 galaxies. But what does infinite space imply for the existence of parallel universes? One possibility is that if the universe is infinite, then there are regions of space that are identical or very similar to ours, simply by chance. This is because there are only a finite number of ways to arrange a finite number of atoms in a finite volume of space. Therefore, if the universe is large enough, there will be repetitions of the same or similar arrangements. For example, there could be another planet that looks exactly like Earth, with another you living on it. Or there could be another galaxy that looks exactly like the Milky Way, with another solar system that looks exactly like ours. Or there could be another observable universe that looks exactly like ours, with another history and another future. These regions of space are called the level I parallel universes, and they are separated by vast distances that are beyond our reach. Another possibility is that the universe is not only infinite, but also holographic. The holographic principle is a property of quantum gravity that states that the description of a volume of space can be thought of as encoded on a lower dimensional boundary to the region, such as a light-like boundary like a gravitational horizon. This means that the information content of the universe is proportional to its surface area, not its volume, and that the universe can be viewed as a projection of a lower dimensional reality. For example, a three-dimensional object can be projected onto a two-dimensional screen, and a two-dimensional image can be projected onto a one-dimensional line. The holographic principle suggests that the contents of the universe originate as mathematics encoded on a boundary surrounding the entire cosmos. The holographic principle was inspired by black hole thermodynamics, which conjectures that the maximum entropy in any region scales with the radius squared, and not cubed as might be expected. In the case of a black hole, the insight was that the information content of all the objects that have fallen into the hole might be entirely contained in surface fluctuations of the event horizon. The holographic principle resolves the black hole information paradox within the framework of string theory, which is a theory that attempts to unify quantum mechanics and general relativity. The holographic principle has been tested and confirmed in some special cases, such as the ADS or CFT correspondence, which is a duality between a quantum field theory in a flat space and a string theory in a curved space. However, the holographic principle is still a conjecture in the general case, and its implications for the nature of reality are not yet fully understood. One of the implications is that the universe could be a hologram, an image of reality coded on a distant two-dimensional surface. This means that there could be another way of describing the universe that is simpler and more fundamental than the usual three-dimensional description. This also means that there could be another level of parallel universes, where each two-dimensional surface corresponds to a different three-dimensional projection. These are called the level I parallel universes, and they are separated by different dimensions that are beyond our perception. Before we talk about the mirror image universe, we need to understand the concept of CPT symmetry. CPT symmetry is a fundamental symmetry of physical laws under the simultaneous transformations of charge conjugation, C, parity transformation, P, and time reversal, T. Charge conjugation means changing particles into antiparticles, which have the opposite electric charge and other quantum numbers. Parity transformation means reflecting space in a mirror, which reverses the spatial coordinates. Time reversal means reversing the direction of time, which changes the sign of the momentum and angular momentum. CPT symmetry means that the physical laws are invariant under the combination of these three transformations, or in other words, that the physics in a CPT transformed universe is the same as in our universe. The CPT theorem says that CPT symmetry holds for all physical phenomena, or more precisely, that any Lorentz invariant local quantum field theory with a Hermitian Hamiltonian must have CPT symmetry. This theorem was proved by several physicists in the 1950s based on the principles of Lorentz invariance, locality, and causality. Lorentz invariance means that the physical laws are the same in all inertial frames of reference, which are related by rotations and boosts. Locality means that physical interactions can only occur at the same point in space and time, or within a finite distance and time interval. Causality means that the effect of an event cannot precede its cause, or that the future cannot influence the past. CPT symmetry is recognized to be a fundamental property of physical laws, and it has been tested and confirmed by many experiments. However, some of the individual symmetries that make up CPT symmetry are known to be violated by certain physical phenomena. For example, parity symmetry is violated by the weak interactions, which are responsible for radioactive decay and nuclear fusion. This means that some processes, such as beta decay, are not the same when reflected in a mirror. Similarly, charge parity symmetry, or CP symmetry, is violated by some processes involving quarks, which are the constituents of protons and neutrons. This means that some processes, such as Kohn decay, are not the same when the particles are replaced by their antiparticles and reflected in a mirror. These violations of parity and CP symmetry imply, by CPT invariance, violations of time reversal symmetry as well. This means that some processes, such as B-meson decay, are not the same when the direction of time is reversed. However, the violations of parity, CP, and time reversal symmetries are very small and rare, and they do not affect the validity of CPT symmetry. In fact, CPT symmetry is so fundamental that its violation would imply the breakdown of quantum mechanics and relativity, and the loss of causality and unitarity. Therefore, physicists assume that CPT symmetry is exact and universal, and that any theory that violates it is inconsistent and incomplete. One of the implications of CPT symmetry is that there could be a parallel universe that is a mirror image of ours, where the laws of physics are reversed. This is the idea of the mirror image universe, which was proposed by a group of physicists in Canada in 2018. According to their model, the mirror image universe is an anti-universe that extends backwards in time before the Big Bang, and that has the opposite properties of our universe. In the mirror image universe, matter is replaced by antimatter, left is replaced by right, and future is replaced by past. The mirror image universe is connected to our universe by a singularity at the Big Bang, which acts as a CPT transformation. This means that the physics in the mirror image universe is the same as in our universe, but with the signs of C, P, and T reversed. The motivation for the mirror image universe model is to explain the imbalance of matter and antimatter in our universe. One of the biggest puzzles in cosmology is why our universe is dominated by matter, and why there is almost no trace of antimatter. According to the standard model of particle physics, matter and antimatter should have been created in equal amounts in the early universe, and then annihilated each other, leaving behind only radiation. However, this is not what we observe. Instead, we see a universe filled with matter, such as stars, planets, and galaxies, and very little antimatter, such as antihydrogen or antihelium. The ratio of matter to antimatter in our universe is estimated to be about 1 billion to 1. To explain this asymmetry, physicists have proposed various mechanisms that could have generated a small excess of matter over antimatter in the early universe, such as baryogenesis or leptogenesis. These mechanisms require the violation of CP symmetry and the conservation of baryon number, which are the conditions for Sakharov's criteria. However, these mechanisms are not well understood, and they do not explain why the excess of matter is so small and fine-tuned. Moreover, they do not explain why the universe started with equal amounts of matter and antimatter in the first place, and why there is no region of space where antimatter dominates over matter. The mirror image universe model offers a different explanation for the matter-antimatter asymmetry, based on the assumption that the universe is symmetric under CPT. According to this model, the universe started with 0 net baryon number. meaning that there was no matter or antimatter at all. Then, during the inflationary epoch, quantum fluctuations created regions of space with positive or negative baryon number, corresponding to matter or antimatter. These regions of space were separated by domain walls, which are surfaces that mark the boundary between different phases of matter. As the universe expanded, the domain walls collided and annihilated each other, leaving behind only two regions of space, one with positive baryon number, which is our universe, and one with negative baryon number, which is the mirror image universe. The singularity at the Big Bang acts as a CPT transformation that connects the two regions of space and ensures that the total baryon number of the universe is still zero. The mirror image universe model predicts that the mirror image universe is identical to our universe in every way, except for the signs of C, P, and T. This means that the mirror image universe has the same physical laws, the same initial conditions, and the same history and evolution as our universe, but with everything reversed. For example, in the mirror image universe, there is a mirror image Earth, where the continents, oceans, and mountains are flipped. There is also a mirror image life, where the DNA, proteins, and cells are mirrored. There is even a mirror image you, who is made of antimatter, who writes with the left hand, and who remembers the future and anticipates the past. The mirror image universe is a perfect reflection of our universe, and vice versa. We have reached the end of our journey into the parallel universe theory. We have learned that there are different types of parallel universes that scientists have proposed, based on the concepts of eternal inflation, quantum mechanics, infinite space, and CPT symmetry. We have also learned that parallel universe theory has some fascinating and controversial implications for our understanding of reality, ourselves, and our place in the cosmos. But how do we know if parallel universes exist? And if they do, how can we detect them or communicate with them? These are some of the open questions and challenges that physicists and cosmologists are trying to answer and solve. Some of them are looking for experimental evidence or observational signatures of parallel universes, such as gravitational waves, cosmic microwave background anomalies, or quantum entanglement. Others are looking for theoretical frameworks or mathematical models that can describe and unify the different types of parallel universes, such as string theory, M theory, or loop quantum gravity. But what about you? How do you feel about the possibility of parallel universes? How would you feel if you met another version of yourself? How would you know which universe is the real one? What would you do if you could travel to a parallel universe? Would you explore it, or would you avoid it? Would you try to change it, or would you respect it? These are some of the questions and dilemmas that you might face if parallel universes are real. We hope that you enjoyed this video and learned something new and interesting. If you did, please like, comment, and subscribe to our channel, Spaceverse, where we explore the mysteries of the universe. And don't forget to hit the bell icon to get notified of our latest uploads. Thank you for watching, and remember, the universe is not only stranger than we imagine, but stranger than we can imagine.